BRCA1 and BRCA2, or BRCA1 and BRCA2 DNA repair proteins. Vanessa is planning a career in criminalistics, which I find very interesting because my father is a retired police officer, so it rings a bell. This field of BRCA1 and BRCA2 is of course linked to women who are predisposed to breast cancer, so it's a pretty big deal. Is it working?
Yes.
Okay, hello, my name is Vanessa Squares, and just like how Figgy said, I am the last presenter out of the 4 amazing that we just had. Just like they did, I'm going to be presenting my senior research project. But before I get started with my topic, I just have a question or thought to propose to you guys as the audience. Imagine carrying a hidden code in your DNA, one that could dramatically increase your risk of developing cancer. For millions of people worldwide, the BRCA mutation is that code, and it's silently passed down through multiple generations. Now imagine this person is a loved one, such as a family member, a friend, a coworker, or even yourself. For me, this person was my mom. She tested positive with a BRCA2 mutation, and at the age of 40, she had a double mastectomy and an oophorectomy, meaning that she had her breast tissue as well as both of her ovaries removed. And this was to hopefully decrease her already increased risk of developing breast and ovarian cancer in her lifetime. But what if you knew a little bit more about your genetic makeup and your family history? How would this affect your future planning? And this leads me into my topic, which is treating BRCA mutations with PARP inhibitors. So the purpose of this project was to provide evidence to support a hypothesis, and my hypothesis is stated as, do PARP inhibitors delay the return of cancer in patients with a BRCA1 or 2 mutation? And so during this presentation, I'm going to provide a little introduction of what BRCA is, what PARP is, what PARP inhibitors are, and then I'm going to run through an overview of some of the articles that I used in my paper. Before I get started into a real introduction, I have this graphic, which is from a website known as Your Attention Please. And this website aims to bring awareness to cancer, but specifically BRCA mutated cancer types. And as we can see, there's a huge height difference between all of these bars here. The red bars represent those with BRCA mutations. It can be either type, BRCA1 or BRCA2. And the gray bars represent the general population, or those who don't have this hereditary BRCA mutation. So starting from the left here, those with a BRCA mutation have up to a 50% lifetime increased risk of developing breast cancer by the age of 50, compared to the general population who has a 2% risk. In the center, those with a BRCA mutation have up to an 87% lifetime increased risk of developing breast cancer by the age of 70, and that is compared to the general population who has an 8%. Finally, on the right, those with a BRCA mutation have up to a 44% increased risk of developing ovarian cancer by the age of 70, compared to the general population who has about less than 1%. So finally, getting into my topic a little bit, I'm going to explain what the BRCA gene is. So BRCA stands for breast cancer gene, but it doesn't only affect breast cancer. It plays a role in ovarian, pancreatic, prostate, and even melanoma. There are 2 types, BRCA1 and BRCA2, pretty easy to remember. BRCA1 has a few more functions than BRCA2, but they share one function in common, and that is that they are both tumor suppressor genes. So they play a role in the DNA repair process. We all have 2 copies of each of these genes. We get one from our mom and one from our dad. These BRCA mutations are only hereditary. However, those who are not born with the BRCA mutation, their BRCA genes can become damaged over time, just because of age and environmental factors. So I included this image on the left, which lists multiple reasons that determine whether or not someone might be at risk for having a BRCA mutation in their family. So if we take a look, 1 and 2 say that you might have an increased risk if you have a personal history of breast or ovarian cancer. 3 and 4, if you have a family history of breast or ovarian cancer. 5, if you have a relative who is diagnosed with a BRCA mutation. Or 6, if you are of Ashkenazi Jewish ancestry. Now for a quick explanation of PARP. PARP stands for poly-ADP ribose polymerase, or PARP for short. The discovery of the PARP protein was made about 50 years ago, and this protein is activated by DNA damage, and it plays a role in repairing single-stranded breaks of DNA. PARP can even sensitize cancer cells and enhance the effects of chemotherapy. So after the discovery of the PARP protein, they created PARP inhibitors. And the main goal of these PARP inhibitors is to selectively kill cells with defects that come along from these BRCA mutations. And so they do so by promoting double-stranded breaks in DNA. And this can be seen in this image here, which was found in an article titled "The Development of PARP Inhibitors in Ovarian Cancer from Bench to Bedside." This article was written in 2015, so just about 10 years ago, and it was the first article to be published after the approval of the first PARP inhibitor, which is known as olaparib. Olaparib is still approved today, it's still used today, and it is approved to treat BRCA-mutated ovarian cancer. The article also has the main topic of synthetic lethality. Synthetic lethality is described as the selective killing of cancer cells, and PARP inhibitors are a great example of this. In fact, they're the only example of this seen in laboratory research. So just to break down this image a little bit more with what I just talked about, if we take a look at the top, we can see that there's a single-stranded break in the DNA. This is when the PARP protein would usually come in and repair the single-stranded break. However, since the PARP inhibitor was introduced, the single-strand break cannot be fixed and therefore it persists. The single-strand break, since it wasn't fixed, is then converted to a double-stranded break. In normal cells, we have a backup mechanism known as HR, or homologous recombination. And this backup mechanism is error-free, precise, it works 99% of the time, and therefore cells without this mutation can be fixed and survive. However, on the other hand, those cells with the HR deficient or BRCA mutated cells, they don't have this backup mechanism. They have other backup mechanisms, but they only work about less than 1% of the time. They're not very precise, and they are prone to many errors. Therefore, these BRCA mutated cells are unable to survive. So, like I stated, the first PARP inhibitor was approved to treat ovarian cancer in 2015. However, since then, many other PARP inhibitors have been approved to treat other types of BRCA-mutated cancers. The first article here, written in 2018, proposed that PARP inhibitors were a good treatment for breast cancer. And the second article in 2021 proposed that PARP inhibitors were a good treatment option for metastatic castration-resistant prostate cancer. This article even went further to say that BRCA1 mutations have a possible blunting and that BRCA2 mutations are more sensitive to these PARP inhibitor treatments. I included this image on the left, which shows two pie charts, A and B. A represents mutated BRCA1 genes and B represents mutated BRCA2 genes. And as you can see, the second circle has a pink section that the first one doesn't have. And that represents homozygous deletion. So this means that when both copies of the BRCA2 gene are mutated, there is a 34% increase in sensitivity to these PARP inhibitors, which, like I said, is not seen at all in mutated BRCA1 genes. Finally, my last two articles compare the use of PARP inhibitors when used as a first-line therapy versus as a maintenance therapy. First-line therapies are the initial treatment. The most common for cancer is chemotherapy and other types of radiation. However, the article written in 2020 proposed that these PARP inhibitors were to be used as the initial first-line treatment. The second article, written in 2023, used PARP as a maintenance therapy, and patients in this study were previously treated with platinum-sensitive chemo and a PARP inhibitor. After that cycle was completed, the patients then relapsed, so they then reintroduced the same PARP inhibitor, and patients showed to have progression-free survival of up to a year or greater. Finally, as a little review, I explained what the BRCA gene is, what the PARP protein is, and what PARP inhibitors are and how they work. I showed how PARP inhibitors affect non-mutated or healthy versus mutated cells. I proved that PARP inhibitors can be used to treat multiple types of BRCA mutated cancers, such as breast, ovarian, pancreatic, and melanoma. And finally, I described the difference between first-line therapies and maintenance therapies. So, going through my research, I would say that my hypothesis, stated as do PARP inhibitors delay the return of cancer in patients with a BRCA1 or 2 mutation, is supported. My sources and questions.
Is this the mutation in the BRCA gene, is that dominant or recessive, or does it not?
It is autosomal dominant. So if one of your parents has this mutation, you have a 50% chance of also having this mutation.
Can you speculate whether other proteins in this DNA repair mechanism, if they're mutated, would they result in the same phenotype in terms of cancer risk, or would that, if not, would that suggest something about BRCA1 to do?
Figgy, you always get me with these questions. Every time I presented, you've asked me a question. I mean, that's hard to say.
Yeah.
I mean,
I'm curious. I don't.
Yeah. I'm also very curious. I mean, BRCA seems to be like the forerunner in this, so.
So it was a really hard question, but I'm not asking to put you on the spot, but to me, it suggests that BRCA1 does other things.
Yes.
Because you have the RAD proteins and so forth, they are involved in this, and I don't think they are as linked to breast cancer and ovarian cancer as BRCA1, so there might be something. I'm just curious if anybody knows what else.
Yeah, I'm not sure, but that is definitely a great question. Yeah, no, it's okay.
I'll be quiet.
Yes.
How do you get tested?
That's a great question. I don't know. I believe my mom has stated that it's maybe a blood test. I'm not too sure. I believe it's fairly simple testing though. Yes.
Okay, so Chris brought up something that has mystified my family for generations. I'm the fourth generation in the family that lost many, many members due to, it turns out, the BRCA2 gene.
Yes.
Lost a father and a sister, both very young. Another sister has it, but because she had got it later, they were able to treat her appropriately, and she's still with us.
Okay.
So this is, in a way, a big discussion, because there are family members who said, well, I don't want to know if I have that, and I get that, and that's their business, but it was in a way a relief to find out that this wasn't some random thing or a dietary mistake or bad karma, but there's something very real.
Right.
The testing is very easy. All you have to do is go to your local genetic counselor and tell them that you have a close family member who is positive for the gene, and your insurance should normally pay for that. And then you get the interesting and also kind of scary part where you wait for the test to come back, but you have a counselor who supports you through that. And in our family's case, my sister who's positive lives in New Zealand, and at the time when I was tested, I did not have it. I was living in the Lehigh Valley, and the two geneticists talked to each other basically. So the mystery is solved. It's not a fun thing to have. The final piece that we did, which was interesting, is my dad died so young, we now know why.
Right.
Before my mother died, we convinced her to go ahead and get tested in case she might be a carrier. And she didn't want to, she was very resistant. She said, I've lost enough people to cancer, I don't care if I die of cancer. We said, but Mom, all your nieces and nephews and all your children and grandchildren want to know. She was negative, therefore they concluded that it was definitely my father, who has long gone and they couldn't test.
Yes.
So thank you for a great presentation, and thank everyone. I'm so impressed. I love being in the neighborhood of this wonderful institution and a product of it in some small way.
Thank you. Thank you for that thought. That was great. Yeah. Thank you so much. Yeah. No, that's definitely a question that a lot of these people ask is like whether they would want to know whether they have it. I mean, it's a question I think about all the time. Like, I know my mom has it. I don't know if I have it. So the thought of getting tested is a little scary, but if it could prevent or help me in the long run, then I think testing is a great way to go. So that was a great thought. Thank you so much. Thank you.
Thank you. We have time for one more question.
What's the earliest age that you can be tested? Is there an age?
I'm not sure of the age, but like she had stated, some of these people with the BRCA mutation, they pass away at a very young age. It's very, out of the blue. Like I said, my mom tested at the age of 40, so I'm sure like I said, I also have an aunt who passed away, I believe, at the age of, in her early 30s, so maybe starting at 30, I don't know the exact age, but yeah, I could get tested right now, and I'm 21, so.
Well, it sounds like, as with all cancers, it's always good to be on the early side and the late side.
Yes.
So the sooner you learn, the better the chance of being able to treat someone treated. I would also assume that the blood tests would be fine because all you need is DNA and
Yes.
authentic DNA in blood. So,
It is a blood test.
yeah.
But if you do test positive, they will watch you like a hawk. I know people in our community whose children are young adults who are positive, and they're in a complete program of surveillance.
Yeah.
And also with this research, you're gonna have a cure, you have a treatment.
Yes.
So you might as well know ahead of time and,
Yes, I
protect
agree.
yourself.
Yeah, thank you. Thank you.
That's very good. Thank you so much.
Thank you.
And, I have a request for the presenters and the science faculty if we could all get together outside